Physics Bits, a science podcast in English by the grade 11 students of Notre Dame de Sion.
Alright, so we're back for another episode of Physics Bits. Two new students this time from our grade 11 class who are going to talk to us about one of the more interesting and unique figures of physics in the 20th century, Richard Feynman. So, do you guys want to introduce yourselves?
I'm Rose.
And hello, I'm Basile.
So we have Rosa and Basile who are going to talk to us about Feynman. So how about we start as usual with a little summary about who he was, what he did, just no technical details necessarily, just to give a general outline. Who wants to start? Rose, you want to start?
Yes.
All right.
So Richard Feynman was born in May 11, 1918 in Queens and died in 1988 in LA. As a child, he already had talent for engineering and in fact, he maintained a whole experimental laboratory at his home. An IQ test administered in high school estimated his IQ at 125 high, which is pretty good.
Yeah.
When he was 15, he taught himself advanced maths like trigonometry, analytic geometry, or infinite series. While he was still very young, he even joined the Manhattan Project, which is the American atomic bomb project undertaken during World War II.
As a short side note, we had one of our other students from the grade 12 class. They did a whole presentation on the Manhattan Project. So if anybody's interested, you can go and listen to the episode, right? We'll do a little in-house advertising. Go ahead, Rose, continue if you want, or Basile.
In 1965, he won a Nobel Prize for his work in quantum electrodynamics, and he contributed to science in a number of different ways, including the development of what are called Feynman Diagrams.
Yeah, which Basile tried to teach us in 10 minutes in English, and it was very difficult.
But in addition of being a great scientist, he was also a great teacher and a great explainer. And in fact, one of his nicknames was the Great Explainer. So
he's very well known also effectively for his teaching. He taught a very famous course at Caltech. And his course notes, most physicists, they have it at home. I still use it when I want to think of new ways of teaching something that you guys might have in class. Very, very original, and he's very much a physicist. So he was very good at math, but he's a good, very physical intuition. Maybe Basile, you're going to give us a short summary of sort of what he talked about in his life, in his research. I think Rose mentioned quantum electrodynamics and some Feynman diagrams. I know you like those a lot.
Yes. So quantum dynamics is electrodynamics is a very tough subject, but I try to explain you what I understand from this subject. So it's a theory that explains how electrons interact, and apart the gravitation and the radioactivity, it's one of the most important law which explain the phenomenon in the universe.
Right. So just to make a short summary, we learned in grade 10 that we have basically 4 fundamental interactions. Like you mentioned, we have gravitation, we have stuff related to radioactivity, we also have stuff related to the way the atom stays together, so the weak and the strong force. And the other fundamental interaction is what we call electromagnetism. And we're going to have another group talk about James Clerk Maxwell, who's famous for what he did on electromagnetism in the 19th century. So what you're saying, quantum electrodynamics is like the theory of electrons and electric and magnetic fields, but at a quantum scale.
Yeah.
Okay, so I'll let you continue.
And then Richard Feynman found a way to represent the electrons' interactions, and it's called Feynman Diagram.
Yeah.
And because electron and positron can interact with photons, which are particles from another field.
Right, the electromagnetic field.
Yeah, exactly. And our universe doesn't evolve just like one of the Feynman diagram.
Mm-hmm.
It evolves like the superposition of every Feynman diagram at the exact same time.
So the idea being that each Feynman diagram represents one way that they can interact.
Exactly.
But with quantum theory, there's an element of probability. So we don't say things happen concretely. We sort of say this is the probability of this happening, this is the probability of this happening. And so what you're saying is with Feynman diagrams, we sort of do the calculations of all these interactions by taking all the different types of interactions corresponding to different diagrams and then sort of mixing them together and sort of making some average of all that sort of thing.
Yeah.
Okay.
And it is the hardest thing to understand with the quantum's mechanical theory so far. I found it very difficult.
Well, I think it's normal that you find it very difficult because technically you shouldn't be doing it before at least 4 more years or 5 years. It's part of what we call quantum field theory. So you guys have seen fields, I think, in physics this year, right? Yeah. So fields is a very general notion we use in physics. And when we talk about quantum fields is the idea of fields, but at that scale of the atom or the quantum scale, as we call it. So he's very much known for these Feynman diagrams, which made the calculations much easier. Yes. For these kinds of things. Did you guys find what else he sort of maybe worked on or what else he's known for, anything that he's famous for in general? Because he did a lot of work, obviously, but...
we just find this work and the fact that he's a very good explainer.
Yeah, so he was an excellent teacher, not only as a teacher to students, but also in explaining to other physicists or taking notions that were very complex and making them understandable. So let's go to some of the questions that your classmates had. There were a few in there. So you already answered one. What is this whole quantum electrodynamics, what we call QED? Did you guys find any fun facts about Richard Feynman?
I know that he was a late speaker and he didn't speak until 3 years old.
I didn't know that. And then when he spoke, he talked about quantum fields and and trigonometry. So he's like I was telling you guys before. He's very well known. He's very what we call bigger than life in that he was interested in a lot of things other than just science, and he had a very charismatic presence. Did you guys find any interesting quotes from Feynman? I know you were shaking your phone just before to try to hope to make it come back as you'd found one. Did it come back?
Not really.
Not really? Okay, so do you guys, you didn't find any particular quotes that you had found interesting? No?
I think that it's you must not fool yourself and you are the only person to fool.
That's very good. So there was one question, I think somebody who tried to understand your presentation on the Feynman diagrams and who had some issues with it, put a question: why is it that in this theory some electrons go into the future and some of them go into the past? Okay. So in fact you did talk about some electrons that go to the future and some that go to the past, and there's positrons and there's weird stuff happening. What is all that about?
So it's a bit difficult and I didn't really understand it, but I can explain or try to explain.
Yeah.
It's electron and positron are defined by a complex number and a phase.
Yeah.
So the complex number is different for every electrons and every positron, but the phase change, and that's how we can know if it's an electron or a positron, because when it's an electron, so the phase were represented by a circle of colors, and when the phase change, the color also change.
Okay.
And the phase turn clockwise for the electrons, and for the phase of the positron, it turns counterclockwise.
Okay, and so this sort of representation corresponds to the idea of moving in time? Is that the idea?
Yes, it's when electrons and positron moves in space-time, the phase change.
Okay. So I think it's, as you said, a very, 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 very complicated thing to talk about without any equations, and even with equations, even more difficult. But I think in general, what we want to think of in science is that, in physics, is that so time, while we, as in our general experience, we can only go forward in time. We can't go back in time, despite what some of you might want. We can only go in one direction, but the laws of physics is what we call symmetrical in time. That means that there's nothing in our equations which have time as a parameter, which tell us you should be going in this way or that. We can change the direction. And so what we notice is that you can take an equation that describes an electron going forward in time, and sort of the same equation corresponds to the description of what we call a positron, which is the anti-electron going backwards in time. So what does that mean in and of itself? Well, that's a much more complicated question, but at least in terms of the equation, that's how it is. Okay, well, we're nearly done. So did you guys find anything else that you might want to bring up, or you found, I suppose you found it difficult researching Feynman,
but
because
very interesting, because it's the first step in quantum electrodynamics. So it was
and what his contributions to 20th century physics are among the greatest. So, and he's a very interesting and funny and fun character. Okay, well, that was a really good job for something that's kind of difficult. So thank you very much. So thank you, Rosa and Basile, and we'll be back next time with another episode featuring a new scientist. Thank you very much.